Okay, good morning everyone. This is Intermediate Dynamics. And, my name is Satya Singaraman. First of all, am I audible to all of you? Okay, I did bring a mic, but I think this is a small enough room that I don't need to use one. Okay, I'll write out my name and yes, please come in. Has a very bad design. This thing here is going to completely block off this side. So if you are unable to see what I'm writing on the chalkboard at any point in time, please let me know. Okay? Alright, so that's my email address, .11. Please email me at osc.edu. And not on Buckeye Mail, because Buckeye Mail is not officially supported by the department or faculty, so my replies might be slower here. Okay? Okay. What I want to do today is briefly go over the syllabus, talk about some salient points on the syllabus, and then we will dig into the world of dynamics. Okay? All of you are able to access my Carbon page. Okay, so you might have taken a look at the syllabus there. Yeah. I want to mention a couple of things in terms of the resources and so on. Okay. You will see that I have listed, let me start off with the textbook. We don't have an official textbook for this course, okay, because there are many different sources that I typically take my material from. Okay. But if I were a student who wanted to study dynamics deeper, and I want to buy a book of some sort, I would recommend the book by John Taylor, which is called Classical Mechanics. Classical Mechanics. This book is not mathematically deep, which could be a benefit in some sense, but it has quite a good depth of conceptual ideas in there. Okay, so it's a reasonable book to have. The book that we will be very closely following in many ways is the book by Oliver O'Reilly, which is called Intermediate Dynamics. Intermediate Dynamics. In fact, he has an interesting book which is a slight step down from this book, which is called Engineering Dynamics, a Primer, which is not a bad book to have if you're looking at some of these concepts. So, same author, much more approachable book. This book is quite tedious in terms of the math and so on. So I will not go too deep into the math that this person talks about in their book, but we will of course cover some of these concepts. Okay, same author, Engineering Dynamics, a Primer. It's a very thin book, but it packs a lot of punch, a lot of information that you should have. Okay. So I would suggest, if you want to buy a book, these are books that you can opt in to buy. I will be posting lecture notes. Sometimes my lecture notes might be handwritten. Most times, I think once we get to a certain depth, I might post out some typed out lecture notes with proper figures and so on. So you should be okay without a book. But if you want to dig deeper, these are certainly good books to have. Okay. All of you able to understand my writing on the chalkboard? All corners of the room, you're able to see my writing? Okay. Thank you. There are other books as well. A couple of them that I have listed on the syllabus by Greenwood. Greenwood is a good author, approachable. Okay, so something to think about there as well. In terms of my office hours, please feel free to ask me questions during office hours. At any point in time, if you have any issues, certainly feel free to email me. Okay. See, we're getting a packed room here. That's good and bad in a sense. So please do not hesitate to reach out to me if you need any help in terms of the concepts, the material, and so on. Okay. I have office hours on Fridays, 10 to 11, and then I have office hours from 4 to 6 in the evening. All of them will be conducted online via Carbon Zoom. So feel free to stop by. Even if you do not have any questions, if you want to just sit during office hours and think about the concepts, maybe go over what we have done in class and then ask me questions then and there, that is also completely fine. Okay? I anticipate that we will have a lot of conceptual questions that come through the study of dynamics. Okay? And no question is a foolish question, no question is silly or anything of that sort, so please do not hesitate. If you have a question, just go for it. Okay? Alright. In terms of grades and so on, this is a technical elective, right? Which means that my approach to grading, and I'm your grader and I'm your TA as well. We don't have a grader for this course. My approach to grading is kind of holistic. I want to see your effort in the class. Okay, I want to make sure that you are understanding dynamics. We will try our best to make it very interesting. Dynamics is interesting. Things move with time, right? So what is not interesting about it? The passage of time. I want to see your best effort. The problems in the homeworks will be difficult. This is not by design. This is because they are challenging problems. And once you solve challenging problems, then other problems become easier. They become much more simpler to handle. Okay? The problems will be mathematically deep in some sense. So that's also another area where I would like to see your best effort in them. Okay? You have, I think, 5 homework assignments throughout the semester, and about a couple of midterm exams, and then a final exam. Each of the homeworks, I have spaced it around so that you have at least a couple of weeks between the homework assignments, because you might need it. Okay? I will make sure the problems are not grunt work problems. They are interesting problems where you will, at least it will stoke your curiosity in some ways to be able to solve these problems. Okay? All the exams are take-home exams. The final exam is over a period of 3 days. Does not mean you will require 3 days to solve it. Midterm exam is over a period of 1 entire day, which also says that you don't need an entire day to solve it, but they will be, quite a challenge. Give me your best effort. Make sure you're being above board in terms of academic misconduct and so on. Please make sure you're staying on course. Yeah. I trust you that you will try your best, and you will also be practicing the policies of academic conduct. And during exams, I will not be available for any questions. That's something I want to say outright, because I want to be fair to everybody. So you can't ask me questions during the duration of the exam, but before and after, certainly anytime you have questions, email me. Email is the best way to get in touch with me. You can ask me questions maybe after class as well. That's not a bad idea too, as long as we keep our distance. Office hours, always welcome. Make sure you are understanding the concepts. Some of these things can be too mathematical, and one can get lost in the math. We don't want that to happen. We want to understand them in a much more deeper manner. We want to understand the physics of it as well. I think that about does it for the basic administration of the course. My anticipation is that pretty much all of you will do very well in the class. And to date, I have not seen a grade lower than a B+ in this course. If that's any indication of how people perform. Okay. In terms of, do you all have any questions, please? Any questions or clarifications? Typically for your homework, you might have 4 to 5 problems, 4 to 5 long problems. I will be grading your homework, so I will pick one problem to grade from what you have submitted. You will not know which problem I will be grading. So you will have to give your best attempt on all the problems. Whatever problems I don't grade, I will just grade you on effort. Okay, so if you put in the actual effort in trying to come up with an answer, you should be in good shape. Okay, so topics is where I think my interest is mostly the administration and all that you already saw in the syllabus. So in terms of topics, here is the order that I think I will be following this semester. A bit on the history of the course. So I developed this course in 2014 and it's been offered every year since then. It's a technical elective. The first time I offered this course, there were 3 people in class. So this is a step up from there. So it says that more people are interested in dynamics, and that's really nice. Okay. This course is called Intermediate Dynamics, but there is nothing intermediate about dynamics. Dynamics is dynamics. Many of the topics that you see in this course also belong to a graduate course called Advanced Dynamics, which I teach with my other colleagues. So it's not as if this is just a step above ME 2030. This is on the same level as Advanced Dynamics in many ways. Okay. And in terms of the topics, here is my organization, and it sometimes changes depending on class participation, depending on student interests and so on. But here is my order of thought. Okay, so I will first go over the Newtonian formulation. We will be looking at 3D motion, okay, so 3D particles. Because in 2030, I believe, you would have seen mostly only 2-dimensional motion, right? So here there will be more involved concepts. Then once we do that, we will look at 3D rigid body dynamics. And I might probably not use the Newtonian framework for this. I might approach it from the Lagrangian perspective. So it is possible that we might do 3D particle motion using Newtonian framework, and then we will move on to what we call as analytical mechanics. Okay, so analytical mechanics is a broad terminology given to a branch of mechanics where you make use of energy-based methods, predominantly among them the Lagrangian framework. Okay, so here is where we will look at the Lagrangian framework. Lagrangian mechanics, and we are going to approach this from 2 sides. First side is we will use the calculus of variations to look at how the Lagrange equations are developed. Okay? So variational calculus. This will give you the conservative Lagrangian equations, which means that it will not account for friction or any kind of dissipation. Okay, and you'll see why that is the case. This is the approach preferred by the physicists. Typically, they don't deal with things like friction that we engineers spend a lot of time thinking about. But we obviously need to include friction in our equations, right? So how do we do that? There is a more general classification using the principle of virtual work. This is the second way that we will approach Lagrangian mechanics or analytical mechanics. And we will also spend time seeing, okay, how do these equations eventually come about, okay, how the Lagrange equations come about. And if we have time, I want to go into the study of chaos. So probably the last thing that I might end up doing is, if there is time, okay, most of the times there is time, so we will look at it. And using these methodologies, the Newtonian framework is something that you're used to based on undergraduate dynamics. Maybe some of you have already encountered the Lagrangian framework, which is good, which means that we will build upon that, or we will strengthen that aspect. Okay. So using these two frameworks, we will look at some of the seminal problems in dynamics. Two fundamental problems. One is the rolling coin problem. Okay, so that's the first problem that we will look at. And then the other problem is the symmetric spinning top. These are the most general problems that you will come across in dynamics and 3D rigid body dynamics, essentially. And in between, we will have lectures where we will also look at bifurcation analysis. Okay, that is when you look at stability of systems, stability of bodies, and so on. There are situations where there is a certain parameter, and if you vary that parameter, perhaps the system is stable, but if not, it is unstable. So we will look at such things as well. So I'm running out of room to write on here, but bifurcation. We will restrict ourselves to one dimensions here. It will be studying the equilibrium points and so on in bodies. So we'll talk about it when we come there. So bifurcation and stability analysis. And there are different ways of studying stability. Perhaps you might have seen stability analysis in system dynamics, probably system integration and controls if some of you have taken it, some of you may be taking it now. So what we will do here is slightly removed from it, slightly different from it, but they all eventually fall into the same sea, the same ocean. Okay, it's just another tool. All right. So I hope this looks appetizing to all of you. It is challenging material, which means that I will take my time going over some of these things. It is quite possible that we might end up spending a good amount of time on derivations. They are necessary because that is the best way to learn how these equations come about. Okay? And I am not a believer in using formulae. So for every problem that we solve, we will be deriving everything from scratch. And that is the approach I want you all to take as well. Okay? You might have seen the acceleration formula or the velocity formula in dynamics. Coriolis, components, and so on, all those things. And then you will remember them or write them up on a piece of paper and then try solving problems using that. But that does not produce the right mentality to approach problems in general. So how do we attack problems in general? That's the approach that I want to take. All right. So any questions? Or I guess there might be lots of questions because we haven't gone over any of these things yet. Any general comments before we begin our actual lecture? All of you still able to hear me? Okay, writing is legible? Okay. All right, so what I will do today is we will look at a nice problem because I want you to understand my mentality in solving problems. Okay, so we will look at a problem of an inverted pendulum. I'm pretty much sure most of you or all of you have come across a pendulum of some sort. So I'll be looking at an inverted pendulum, which is a fundamentally unstable system because the flow is just going to fall off. The inverted pendulum, the human body is an example of an inverted pendulum. So we are walking here. I am a pendulum that is actually moving back and forth in some sense. There are oscillations that are taking place. But we also have a stability mechanism which is wired inside our brains that enables us to control our instabilities. We will not go into those aspects here, but I will at least look at the general equations. Okay? And in doing so, we are going to come across this very, very important thing, which is called as the time rate of change of a unit vector. And if you understand that, then pretty much all the problems that we're going to solve will be fairly straightforward. Okay? So let's start off with the problem, and in the process, I will introduce you to time rate of change of unit vectors. So some sample problem. This is just to get us used to each other's way of thinking. Okay? So I have an inverted pendulum, two-dimensional. This is my x-axis, y-axis, z-axis out of the plane of the board. Whenever I write unit vectors, I want to use the following notation. Okay? Unit vector along the x, y, and z frame, which is going to be called from now on as the fixed frame of reference. So this is a fixed frame of reference. That is, this frame does not move. It is just stuck to the board. Okay? The unit vectors attached to a fixed frame will always be called by me as I, j, something that you might have come across in dynamics. I hat, j hat, and k. Okay? Whenever you have a fixed frame of reference, you're going to have an observer. An observer is a person. You can think of an observer as yourself. If I have an observer on a fixed frame, then that observer is called as a stationary observer. Okay? So I'm going to call that point as some point O. So point O is a stationary observer. Which means that the velocity of this observer is 0. Acceleration of this point or this observer is also 0. Okay? Then I take an inverted pendulum. Essentially I just take a rod, pin it to this stationary observer. Okay? So here is a rod. This is a rod, let's say, of length L, capital L. This rod has a mass M. So rod of mass M and mass moment of inertia. We're going to spend time thinking about moment of inertia. We're going to see how these general equations in Newtonian mechanics themselves come into play. Okay, so for the time being, I'm going to assume that you've come across the idea of inertia, mass moment of inertia, but we'll dig deeper into the antecedents of mass moment inertia. About an axis parallel to the plane of the board. Parallel to the z-axis. I'm going to call this term as Ig, where G is the center of mass of the zone. So G is sitting right at the center. So G, this is L. And if it's a uniform rod, then you know that Ig is 1 by 12 ml square or something like this. Not too worried about it. what I want to do is I want to come up with the equation of motion of this rod. Okay. Equation of motion. And my shorthand notation for equation of motion is EOM. Which tells me that first of all, I need to define what is meant by the equation of motion. Can anybody, have you come across this term first of all? Most of you may have, some of you may not have, that's completely fine. What is an equation of motion? Yes?
It's an equation that describes the position of the pendulum.
Absolutely, it describes the motion of the pendulum. Mathematical model of the motion of the pendulum. Okay, so equation of motion is the mathematical model of motion. So before I do that, we have a good amount of work to do before we even start describing how the dynamics of this body takes place. So here is my procedure to start any problem. The first thing is I write out what are called as the configuration coordinates of the body. Okay? CC, configuration coordinates. This is also a terminology some of you may have come across, maybe some may not have, so I'm going to describe it. This is the total number of coordinates that we need to describe, which will give me the position of this rod at any point in time. Okay, so total number of coordinates. That describe or that prescribe position of the body or a particle or collection of particles, whatever, at any point in time. Most important caveat, in the absence of constraints. Okay? Which begs the question, what are constraints? As the root of the word describes, what are constraints? Constraints are things that limit us. That's exactly what it is. Constraints are things that limit or restrict the movement of the body. Okay? So these are restrictions on motion of the body. And the last thing that I want to describe is called as degrees of freedom. Okay? Or DOF, that's my terminology. Degrees degrees of freedom are the minimum number of independent variables that will fully tell me the position of the body at any point in time. Emphasis on the word minimum. Okay? These are the minimum number of variables that describe the position of the body at any point in time. Okay, so three important things that we typically make use of for every problem that we do in dynamics. Okay. Why are they useful to us? For the following reason. The degrees of freedom are related to the constraints and the configuration coordinates. The number of degrees of freedom is nothing but the number of configuration coordinates minus the number of constraints. And if I know the number of degrees of freedom, then I know that I have a variable that will describe the motion of this body at any instant in time, right? Which is a powerful contributor. So the equation that I want to write out, I think I'll leave that figure there for the time being. Here you go, this one here. So degrees of freedom, number of degrees of freedom is equal to the number of configuration coordinates minus the total number of constraints. And when we go into Lagrangian mechanics, we will call these degrees of freedom as generalized coordinates. At this point in time, we will not label it that way. And the other important thing is the number of degrees of freedom is equal to the number of equations of motion that I expect for the system. The number of degrees of freedom, number of equations of motion. And the very last thing, I need to clarify one thing about the equation of motion. The equation of motion will describe the motion of the body, but the equation of motion should not contain any constraints in it. Okay, so for example, if I am solving for the motion of a block sliding on the ground, what is the constraint on the block? It should not be digging into the ground, which means there is a normal force. When I come up with the equation of motion should not contain that normal force. Why? Is because I don't know what the normal force is until I solve the motion. So that's a caveat that we need to outline here. So the equation of motion should not contain or should be absent of any constraints. Any constraints. Constraints could be pin reactions, for example. So, for example, pin reactions are constraints, normal forces are constraints, as you know. Can anybody name another constraint? Yes. Tension is an example of a normal force. So you can think of that. Yeah. So that's right. You can write this as tension. Exactly when I'm solving for the equation of a simple pendulum, you don't see the tension there. Okay. Any other examples? There's one last creature I haven't labeled yet. is one more thing.
Gravity, is it?
Gravity is not a constant.
Okay, good.
Yeah, gravity is not a constant. Gravity is, we treat it as an external force, or a central force. What is a quantity that is related to the normal force? Friction. And in friction, there are two types of friction, right? Static friction, kinetic friction. The force of static friction is a constraint. Okay, and we are going to see why they are called as constraints when we go into Lagrangian mechanics. So we are going to have a way of saying, okay, hey, if we have such a force, and if this force satisfies this following mathematical equation, then we say that this is a force of constraint. At this point in time, all you have is just my word of mouth. You just have to believe in me until we reach that point. Okay? So static friction is a constraint. All right. So, any questions so far? We have the problem. We haven't solved it yet. Before we do that, we have quite a good amount of things to do. We need to find out what the configuration coordinates are. What are these guys? What are those guys? Okay? What's the variable that defines the degree of freedom? But in the meantime, are there any questions? Is my pace of writing okay with everybody? Not too fast? Okay. Right, so I'll take off this. Alright, so let's start off with our problem now. Before I go ahead and look at this problem, I want to draw another coordinate frame, which is going to be attached to the body or the rigid rod itself. So this is a rigid rod, by the way. This is not a deformable rod. So we will not be looking at deformable body dynamics. We will be looking only at rigid body dynamics. That's something I want to clarify outright. Okay, so that's a whole different field by itself. So I want to attach a frame of reference which is going to be traveling with the body. It's called as a rotating frame of reference. And there are many different choices. In the next lecture, we are going to see one of the most fundamental frames of reference, which is called as a Frenet-Serre frame, or what you know as a normal tangential frame. At this point, I'm going to use what I call as a radial frame of reference. That is, I'm sitting here. This was a point on the stationary frame or a fixed frame of reference. From here, I draw a unit vector that is pointing towards the center of mass. Okay, so it's attached to the body though. So I'm going to call this as E suffix r. It's a radial line from the stationary observer to the center of mass. The rod is falling in the following sense, right? If I give it a push on the one side, it's going to be falling in this particular sense. If I call this angle as theta, then I'm going to have another unit vector which is drawn in the direction of increasing theta. I'm going to call it as E theta. These are unit vectors. And the cross product of ER and E theta, I'm going to call it as E suffix z. And the cross product is done using the right hand rule. So fingers of my right hand aligned with ER. I fall towards E theta. The direction of my thumb is going to give me the third vector in this frame, the third unit vector in this frame. Once again, fingers of my right hand aligned with ER. I fall down in the direction of theta. My thumb is pointing into the plane of the board. That's going to be my third unit vector. Okay? I'm going to draw it with the dotted line. I'm going to call it as E suffix z. And I'm going to introduce you, or some of you may already know this, but the triad notation. Okay? So ER, E theta, E z, they are a set of unit vectors that are attached to the body. What is the body doing? This is a body that is not translating, it is rotating, which means that this set of unit vectors are a rotating set of unit vectors. Okay, so rotating along with the body. And they are called a triad. And a triad is a set of three unit vectors which are mutually perpendicular to each other. Please notice my symbol for perpendicular. Can everybody see there, or is it a little tough to? The bottom is tough.
Yeah, a little bit.
Okay, so I might have to. Until here, is it okay? Okay. So I'll avoid writing below that line. So these are a set of unit vectors that are mutually perpendicular to each other. And I want to continue here. ER, d theta, easy. They satisfy the following mathematical rules. ER cross product with d theta gives me easy. They are mutually perpendicular to each other. So if I have to generalize them, then I would say the following. EI cross Ej is equal to Ek, where I, J and K are subscripts which are not equal to each other. I not equal to J, not equal to K. So I could be R, J could be theta, then Ez is defined as ER cross E theta. I can define it whichever way I want. I can define E theta and ER cross that with Ez. But the direction of the unit vector is going to come out of the page. You see that, right? Okay. Then the other rule is that Ei dotted with Ej is 0. So they are mutually perpendicular to each other. That's what the dot product of 0 means. Which means that they are what is called as an orthonormal basis for the problem. Orthonormal basis vectors. And as a matter of fact, I, J and K are also orthonormal basis vectors. I is a unit vector, K and J are all unit vectors. If I cross product I and J, I get K. If I dot I with J, I get 0. Okay, so that's one thing. Now, whenever I write a triad, this is the notation that I use. ER crossed with E theta in my problem gives me EZ. Which means that if I take any other unit vectors here, let's say that I take EZ, EZ crossed with ER will give me E theta. And likewise, if I do ER, EZ, if I go against this clockwise notation, I get the negative of E theta. Does this make sense to everybody? Once again, these are three unit vectors. I have defined, this is we have defined. Tomorrow I can come and say, okay, E theta cross ER is easy. How will my triad change? Instead of writing it as ER, I will write it as E theta, ER, and it will be easy. Okay? So we define the third direction using two mutually perpendicular unit vectors, and once you have defined the third direction, the third unit vector, then this is your triad. And whenever we do cross products, we will always be referring to this triad. We will not be doing any determinants and all that kind of nonsense. Okay? So we will be using only the triad. Are there any questions so far? Everybody go to the triad? All of you are understanding it? I choose a unit vector. That's a choice. So this is a choice. Then I have the right to choose another unit vector. I just choose this to be the second unit vector. It is chosen in the direction of increasing theta. Okay, this is also a choice. If I choose 2, I don't have a choice on the third. But I have a choice on which direction I want the third to be. If I say that, okay, ER cross d theta is the third vector, then that third vector is going to be into the plane of the pitch. If I say the opposite, the vice versa case, if I say I want to do E theta cross with the ER, then EZ is going to come out of the pitch. Why am I choosing one versus the other? Completely arbitrary. But there is also a certain amount of foresight involved in this, because if I look at the angle theta, and if I look at the rate of change of this angle, that is going to give me the angular velocity of this body, or at least one of the components of angular velocity. And I see that in the direction of increasing theta, theta dot is the angular velocity, and that's pointing into the plane of the body. It's pointing along the positive EZ direction. So that's the reason why I said ER cross ET, and not otherwise. Okay. So far so good? Alright, now we go back to our problem here, and we start writing out the configuration problems. Alright, so what are my configuration problems? What do you think it could be? What is the definition of a configuration coordinate? They tell me the position of this body in space at any instant in time without looking into the constraints of the problem. So what are all the things I need to know where this rod is at any instant in time? Assume that this rod is not pinned here, okay? Assume that this rod is not in planar motion. What are the coordinates that you think you will need?
X, Y, Z, and then 3 angles?
Absolutely right, absolutely right. So I would need X, Y, and Z, which is the location of the center of mass. Okay, so if I label this as X, this is Y, and it's on a constant Z plane, right? It's a planar problem. So location of the center of mass. The center of mass is G for us. Then I need 3 angles, one of them theta that you see here. Then I would need 2 other angles because this body can spin about the ER direction, right? So I'm going to call that angle as, this is a rotation, so this is, let me call that as an angle phi. So I need an angle phi. And I need another angle because this body, if it is allowed to move freely in space, it can also spin about the E theta direction. Clockwise or counterclockwise, I don't know. It really doesn't matter to us. Let me call that as the angle psi. So theta is the rotation about the EZ direction. Then phi and psi rotations about the E theta and the ER. And since these are rotations, I'm going to put a dot on top because they are going to change in time. So this is theta dot, phi dot, and psi. Dot is derivative with respect to time. I'll write it down somewhere here. If I have one dot, one derivative with time, 2 dots, 2 derivatives. Okay. So the number of configuration coordinates are 6. How many constraints do you think this problem has? Yes, yes.
5.
5 constraints. Very nice. Why did you say 5?
The pin fixes W or X, Y, and Z, and then you have 2. You also do limits 2 degrees of freedom in rotation.
So it reduces 2 degrees of freedom in rotation. Okay, okay, very good. So 5 constraints. Let me list them out mathematically. Okay, equations. First constraint is that motion is planar. Z is constant. Then the second constraint is that because motion is planar, I cannot have rotations phi dot and psi dot. So phi dot is 0, psi dot is 0. Because the pin is fixed to the stationary observer, so I'm taking a material point on the body. A material point is any point on the rigid body. I'm taking a material point on the body, and then I'm fixing it to the stationary observer, which tells me that the x and the y variables will be related to the angle theta. So pin is fixed. Which tells me that if I look at x, and if I look at the definition of theta, x is sine theta times L by 2. L by 2 cosine theta. I hope all of you can see that. L by 2 sine theta and L by 2 cosine theta. So which tells me that the number of constraints that I have are 1, 2, 3, 4, and 5. The number of constraints is 5. So the number of degrees of freedom, configuration coordinates minus constraints is 1. And you automatically know what that variable is going to be. That signifies the degree of freedom here. -5. Does this make sense to you? This is the procedure I will adopt for every problem I solve. It is quite boring, but it is the best way to do these problems. There is no guesswork here. Okay? So number of degrees of freedom is 1. So what is the best variable that prescribes this degree of freedom? That's something that experience helps. Or looking at the problem and seeing the motion of the body also helps. If I look at this here, I see that theta is a good candidate for a degree of freedom. Okay? So the degree of freedom is theta. If I know theta at any instant in time, I know the entire history and geography of this rod, essentially. So the number of equations of motion I expect one equation of motion. An equation of motion in rigid body dynamics will be a second basis question.
So does the exclamation point mean anything mathematically, or just like?
Okay, can you say that again?
Does the exclamation point behind theta, does that mean anything mathematically?
Oh no, it doesn't. It does not. I was just excited to see.
Okay.
Right. So the equation of motion, things to clarify here, will be in dynamics, rigid body dynamics, will be a second order ordinary differential equation in the degree of freedom. Okay, so this will be a second order ODE, ordinary differential equation. We don't expect partial derivative, partial differential equations in rigid body dynamics. We do expect it in deformable body dynamics. Second order ODE in the variable theta. This could be linear or non-linear, I don't know really. If it is non-linear, it is more exciting. If it is linear, it's quite boring. But many problems give you linear equations. Okay? I want to see if there are any questions so far. It's a fairly methodical way of whittling down all information that is useless and coming to the target variable that we are interested in, which is in this case theta. Okay? The equation of motion is going to be a second order ODE in theta. This equation of motion should not contain any constraints, which means that none of these spin reactions will be playing a role in this problem. Okay? Alright, so now let's get into the real dynamics of the problem, which means we start off with kinematics. So before I look at how the equation of motion is obtained, we need to know the kinematics of the body, which is, can I describe the position, the velocity, and the acceleration of the body in terms of the degree of freedom? This is what the kinematics does. Okay? So let's start off with the position first. I can use any frame of reference to identify the position of the body. I could use a stationary frame and say that the position is x in the I direction, y in the j direction, and 0 in the z direction, or some constant in the z direction. Not very useful, because it does not show me anything in terms of the degree of freedom. So more useful version of the position of the body is by saying, okay, hey, I sit here, I look at the motion of the point G using the coordinates of the rotating unit vector. Okay, so let's do that. So R is the position of the center of mass. So this is RG slash O. Here is my notation. Position of G relative to O. Okay. This is in terms of the unit vectors of the rotating frame. Okay, so this is going to be L by 2 if I assume this is a uniform bar, right? The center of mass is L by 2, and I am looking at the ER direction. Does this make sense to everybody? Sitting at the point 2, looking at the point G, what's the directionality? ER, what's the magnitude? L by 2. Velocity. What is velocity? By definition, instantaneous velocity. We are not looking at average velocity. Instantaneous velocity is the rate of change of the position. Okay, so this is d by dt. Of Rg slash O. So d by dt of L by 2 ER. L by 2 is a constant, L is a constant. So if I do the differentiation, d slash O is d by dt of L by 2 using the product rule, and then L by 2 d by dt of ER. This is 0. So which begs the question, what is the rate of change of a unit vector? And the aim of today's lecture is actually to come up with an expression that gives us the most general way of calculating time derivative of unit vectors. Okay, so time derivative of unit vectors of a triad. Take off this panel here as well. It's okay to do that. Right, so time derivative of a unit vector. So my whole ball game is what is dEr by dt. And by that stretch of imagination, what is dE theta by dt? Because I might come across that too. Okay, so to do this, to understand what these quantities are, and you might have come across this in undergraduate dynamics too, but I want to briefly refresh that memory. I want to look at two configurations of this rigid rod. Okay, so first configuration, sitting somewhere here, so I'm going to draw the unit vectors. ER at some time t. Okay, then this is point G, this is at some time t, then I look at it at a time t plus dt, so a small increment in time. What would the rod do? The rod would have rotated by a small amount. I call that amount as d theta. I'm going to write this guy here. This is the center of mass at the next instant in time, so if I draw the unit vectors, going to be ER at time t plus dt and E theta perpendicular to ER Does this make sense to everybody? Two instances in time. At time t, this is the rod. At time t plus dt, this is the rod. I'm going to take these, and of course, since it is performing planar motion, the third unit vector is always perpendicular to the plane of the ball. It's pointing into the ball. Okay, so I'm not too worried about it yet. When you do 3D rigid body dynamics, we should be really worried about it. Okay? Now, I'm going to take these two sets of unit vectors and I'm going to pin them together by their tails. So, now I'm going to get rid of this figure here. This is the first set, so I'm going to have ER of t. And this is E theta of t. And I'm going to take the second set. I'm just going to move this and pin it to the tail of the first one. But I will still see that offset of d theta. Okay? If I look at the second one, this is ER t plus dt. And this is that. Makes sense to everybody? You can imagine, taking a pair of toothpicks, sticking it onto a potato, rotate the potato. You'll see that the toothpicks are also rotating slightly. That's exactly what I'm doing. And these are the first pair of, these are the two toothpicks at some time t, rotated a little bit, at some other time t plus dt. The arrow that joins ER at t and ER of t plus dt is DER. This is the change of the unit vector, infinitesimal change of the unit vector ER. So this is DER. The arrow that joins E theta of t to t plus dt, because we are moving forward in time, not backward in time, right? So this is now going to be the unit vector dE theta. Am I making sense to you? What's the angle between? D theta. I have two triangles. They're really not triangles, and And in all honesty, this DER is not a straight line, it has to be an arc. Right? Because ER has a magnitude of 1. It's a unit vector. ER at t plus dt also has to have a magnitude of 1. Okay, so in that sense, this DER, I can think of it as an arc length, which is approximated by a very small line segment. Okay, so you can draw it as an arc, almost an arc. So I can write the following expressions. The magnitude of DER, if I think of it as an arc, the arc length is the subtended angle multiplied by the radius, right? So this is magnitude of DER is magnitude of DR at any time t or t plus dt times d theta, which is the same as times d theta. These are magnitudes. This is magnitude. What's the magnitude of ER? 1. Magnitude of ER at t plus dt or t does not matter. So, in reality, we have magnitude of DER is just d theta. This is the magnitude. But it's a vector, it has a direction as well. By the same token, magnitude of dE theta is also d theta. Okay? So this is also the same as that creature. And my whole idea is, okay, how do I write DER by dt? What is DER by dt? That's why I'm doing all these things, right? I'm going to use the chain rule. I'm going to say that DER by dt, first of all, is magnitude times the direction of DER. Right? Fundamental rule in vectors is any vector is its magnitude times its direction. Any vector is magnitude so A is some vector, magnitude of A times the direction. So this is the first thing that I'm writing. Magnitude of DER is d theta. So let me start filling it up here. And keep in mind, V is DER by dt times L by 2. So maybe I need to write that information somewhere. V is DER by dt. And here is what I'm going to say. This is now L by 2 magnitude times some direction. Question mark. Am I making sense to everybody? I don't know this guy. I know this one though, because magnitude of DER is d theta. Right, so this is d theta by dt, so dt slash O is L by 2 d theta by dt E question mark, and here is what I'm going to say. The direction of DER is perpendicular to ER. Why? Very quick, very silly proof. What's this dot product?